Okay, today we're going to start by, I want to just show you for the first time how to use this ODE2 calculator. This is the second program we will be using. You've used slopes already. Now this is the one where you solve a pair of differential equations, a system of two. dx by dt is something, some given function of x and y, with maybe t's in it as well, and dy by dt equals something. The context in which the example I'm going to do will be a special case of a body falling in a very viscous fluid, so it's very slow flow. And so we'll actually use this example, but you will see it worked out in detail with the solution a little bit later on. But I just want to show you the program first. Okay, so what we'll be doing is learning how to program this in, or put it into the software for the ODE2 calculator. Before I get there, I want to make a couple of announcements. First, in sections 1, 3, and 6, Landbo's sections, one of the questions, the question on the radioactive decay, the answers to that were marked incorrectly. And so many of you got it right and lost marks on it. So Landbo will make sure that everybody gets the credit, the marks that are due to them. Right. Did you have a question? Sorry? It was 5 times the half-life. Okay, because, yes. It's probably a good idea, but yes, I mean, if you could do that, that would be good. The second announcement is in connection with the trial, with the real exam, this time next Thursday. It's set, it has 4 questions. Because I let slip this morning that no question will be on the Euler method on the exam, I thought I should let it slip to everybody. So, but there'll be 4 questions. Several have, 2 of them most of them have several parts. Now, it's been my experience that when people do exams, they whiz through the questions, and it looks very good, and then they leave with about a half an hour left to go. Often in those situations, I discover very simple errors, which takes away from the marks that you get. Now, the wonderful thing about differential equations is when you get an answer, you can always check it by differentiating, checking the initial conditions. So, please use every available minute of the full 75 minutes in doing the exam. Do not leave early. That's advice. It's not a hard and fast rule, although it does disrupt your fellow colleagues in the room if you do finish early and get up and walk around in front of them. It distracts a bit. So I would counsel that you plan to stay the full 75 minutes and score the best possible score you can. You will see that actually the marks on these 4 questions add up to 180, whereas the total for the exam will be 200. This is because you will receive after you've finished your exam and you put it up here in under your section heading, you will pick up another copy of the very same exam. And so you can get over a little bit the frustration you felt by screwing up on the question in the exam by redoing it, and you'll get up to 20 extra marks for doing it correctly. It will be due as the homework the following Wednesday. So that's the following Wednesday would be October the 8th. So instead of graded homework number 5 being due on that date, it'll be a retake, as it were, a resit of the exam. Now, I found that this actually is a great learning tool, that even if you do find that when you're in the exam you don't understand something as well as you thought you did and therefore don't get the question right, if you get the chance to go back immediately and try and redo it with a little bit of extra information, then you tend to learn the material quite well. So that's the way we organize this. Let me see, was there any other thing I had to tell you? Oh, yes, the third thing is a little bit later today, I am actually going to go back and revise some of the homework problems on which I've had many questions, and from the TAs have learned that you have a little bit of trouble. For example, we will look again carefully at the question number 2 in graded homework number 4 about the designing the allowed permit rate for controlling a population of rabbits. And because it's an awful pity, in a sense, that you have such tools at hand, but you can't exercise them because you have trouble in solving a quadratic equation and finding the roots of it. So I think we'll pay a little attention to that, because it's very important we get a few of these basics right in order that you can take full advantage of the material you're learning. All right, so we're going to find a little later today y of t will be the position of the mass, or a ball, and y is measured positive upwards, and v is the velocity of this particular ball. And Newton's second law will tell us that mass times the velocity, I mean the rate of change of velocity, if the mass is constant, is the sum of the forces. The two forces will be gravity, which will be acting down, and roughly g is 10 meters per second. I know it's 9.81, but I don't want to deal with decimal points. Okay, so g is 10. Always g is 10 in this class. I'm taking the coefficient of friction here simply just to be 1. So, but this is a case in which it's slow flow, in the sense it's low Reynolds number. Okay, low Reynolds number. It doesn't mean, it means the velocity is slow compared to something else. In other words, the Reynolds number, the velocity times some scale, like the diameter of or the radius of the ball, divided by the kinematic viscosity of the fluid through which it's falling. That is called the Reynolds number, and that is small, or 1, or a little bit less. So we're dealing with a model in which we can model, we're dealing with a situation in which we can model the friction as being opposed to the motion. In other words, if the ball is going up, the friction is down. If the ball is going down, the friction force is up. And it's proportional just to the velocity itself. Now, the solution here, as we'll see, this is a linear first order equation. I'm taking the initial conditions both to be 0, so we just drop the ball from a position y equals 0, just drop it. then the solution would be the v of t is minus 10 times 1 minus e to the minus t. And if you then integrate this to get y, one gets this expression. All right, so now let's take a look at doing it via the via this program. Okay, so for the minute I'm going to turn down the lights while I do this. The particular program that's up here now is for a pendulum or a spring, and we'll be coming to this a little bit later. So now in our case, the dx, instead of the dependent variables, in the program, the dependent variables are called x and y, and the independent variable is t. Now in our case, the dependent variables are y and v instead of x and y. So the x here in the program is our y. So I have dx by dt, in the equation says dy by dt is v. So that is rewritten as dx by dt is y. Now the second equation. The second equation is dy by dt is minus 10 and then minus y. Right? Because the y stands for the v. I'm going to take the time from 0 up to 15. And we'll talk a little bit about the choice of these things in a minute, because choosing these ranges are important. And I'm going to choose this one from minus 100 to 0. So the position is going to be somewhere between the 0 level and 100 meters down, which is minus 100. So you have to remember then the minimum x, or the minimum y in this notation, is about 100 meters down. That's the minimum we're looking at. We may have to change that. And here the minimum velocity, because the thing is going to be falling down, so it's going to have a negative velocity. You can see from the solution that the terminal velocity, after a long time, this goes to 0, and the terminal velocity is about minus 10. And we'll take the top to be 0 again. And I'm going to get rid of I will submit this, and I'm going to get rid of all these things here. And now I have it, this is plotting at the moment. It's got y up this axis and x in this direction. So you can plot this. This has done the solution already. It's plotted y versus x, because you're going to get a solution x of t. X is some x of t, y is some y of t. So you can plot at a particular t the x and y coordinates, but we want to plot y and x versus t, so we hit this to go to the t axis. Now you can see the y has essentially starting from two different positions. Well, let's clear it and come back. Let's clear it, and let's just start. We can just click it with a start here at y equals 0. Oh. So the ball falls down, it picks up speed until it hits the terminal velocity, which in this case is minus 10. Now what would the x look like? All we have to do to plot the x simultaneously is click the x here. Okay, so now we can see this is the ball falling down. This is the x is 0 at the top. We've gone down to minus 100 in the x scale. It's the y scale showing here. So we've gone down, and this is the ball falling down. Okay? Now there's one little wrinkle I'd like to point out to you. What is the slope of this guy? think of this as x versus t. Let me actually, instead of putting the y, I'll put the x as the dominant thing here, this side. So, yes, this is a much nicer picture. So, what is this is y versus t in here, okay? X versus t in the program. So this is the position y as a function of t, okay? Now, you can see roughly it's a straight line. Roughly, what is that equation? What is the slope, do you think? What is the slope? Yes. What? No. No. If you put the negative and the 10 together, negative 10. Right. Right. So because it's falling down. Now I want you to draw in your mind's eye, go all the way back up to the top. Draw that, take the straight line part. Notice it doesn't come back into the 0 point, but in fact, if I were to take this straight line and continue it up until it hit the axis here, I would get 10. So what's happening here is, I mean, for instance, if I go to the y equals 0 position up there, and I draw a straight line from there with slope minus 10, it would be just roughly where my arm is. Notice that at any fixed time here, this y is further down, is more negative than this y here. So why do you think that's so?
Describes acceleration.
Yes, you're correct. At the beginning, you see, it isn't moving at 10 meters per second downwards. Okay, it starts off at 0. So it takes a little bit of time to get up to the 10 speed. If it was going at the 10 speed all the way, okay, if it was going at the 10 speed all the way, it's as if I started it at the position y equals 10 up above here. Y equals 10 feet. Remember we started at the 0. We started at 10, threw it down exactly at the speed 10, so it was at the terminal velocity. We'd end up here on the same track as the particle that started at y equals 0, at 0 velocity, and it took a little time to speed up. And you can see at the top, that little bit of the curve is the time it's just speeding up. So the acceleration is what is displayed in that little curve at the top. But then it becomes a straight line. Okay, now what's sort of important, I'd like you to play with this program a bit, because you'll find, as I often do, that I get my ranges wrong. For instance, supposing I go back and put the old range here on the x, supposing I put it to be minus 10. Now, you see, the program gets, well, it's actually not too bad for that. But what will happen is you have to have it long enough, the range long enough, because roughly speaking, if you're going to run it for 10 seconds, and the thing is roughly falling at a speed of 10 meters per second, by the time you've come to the end of your range of time that you want the solutions for, the thing will have fallen 100 meters. So you better have the range of the x that you're putting in your problem sufficient to reflect that. So these are the things you have to think about in the program. Programming using software is not a mindless exercise. You have to have some idea, as I've preached on and on, you have to have some idea roughly of what the solution is going to look like, so you can pick your ranges correctly so as to get as much information out of the solution as you possibly can. All right, so that's just your first meeting with this program, and you know, you can start playing with that program. using this particular falling body problem just to get used to it. We're going to be using it extensively when we come to the second part of the course, when we're working with oscillators and that sort of thing. All right. All right, so we come back to this little bit later. Now, what I want to do is go back and do this problem of the ecology and touch on places where some weaknesses have been exhibited in some of the homework. The particular problem, and I'll do the one that was on the quiz yesterday as well, but the particular problem we were on graded homework number 4 was if y was the population of rabbits and we measure y in units of 1,000 rabbits. So if we say y is 2, it means 2,000 rabbits. And we're told first that if you put these rabbits on a domain where there's limitless food, so that they can just grow proportional to their number, Malthus's law, I told you then, in that case, that the time it took for the rabbits to double their population was 10 log 2. Did we talk? I think we were years. 10 log 2 years. Rabbits would be quicker than that, though. Yeah. Anyway, that was these are slow rabbits. So 10 log 2 years. Now, how did we get that? So, in other words, the solution of this equation is y of t is y of 0 e to the kt. I told you that the time, t2, taken to double the population, okay, so at t2, the population is 2 times y of 0, and that's equal to y of 0 times e to the kt2. This means that kt2 is log 2. But I told you that t2 was 10 log 2, and so that's equal to log 2. The logs cancel, so k is 1 over 10. And the units are inverse years. Why? Because, take for instance this exponential function, e to the kt. The exponent of an exponential function, in order for something to be something you can calculate, has to be a pure number. Independent, unitless. So if t has the units of years, this guy has to have the units of years minus 1 over years. That's true. See, you can see that from the equation too. If you look at the units of this, it's the number of rabbits measured in thousands divided by years. So this is the number of rabbits, so this has to be 1 over years. All right. Then I told you that, okay, if the rabbits' population grew enough, the environment was limited. And so that the rate of growth, you could think of this as it's growing proportional to y, but the rate of growth, instead of being constant k, is k times 1 minus y over 2. So the rate of growth is slowing the closer you get to y equals 2. It's the saturation point. Y is 2,000 rabbits. That's the number that this particular environment can support. So if we were analyzing this, and we know now k is 1 over 10, we've been told that. If we were analyzing this equation, what would we do? We would draw the graph. We would draw the graph of the right-hand side, and the graph will look something like this, down like that. This is 0, and this is 2. So this is the graph of the right-hand side. This is the graph of 1 over 10 y, 1 minus y over 2. And now we see that it has 2 zeros. 1 is here, 1 is here. If I start, let me get red pens for, yep. If I start anywhere, with any number of rabbits, dy by dt is positive, y increases all the way up till it gets to 2, where it stops. If I happen to have more rabbits at the beginning than 2,000, then the number of rabbits decreases, because effectively this is negative, and so I end up again at 2. So 2 is an asymptotically stable equilibrium point. What is its basin of attraction? Yeah, every y. All y's between 0 and infinity. Doesn't matter where you start, no matter if you had started with, no, you couldn't start with 1 rabbit, because that wouldn't be quite, 1 pair of rabbits, okay? Or if you started with millions of them, you'd end up with the 2,000. Now the thing is, they're beginning to eat too much. They're beginning to eat the flowers, or irises, or very special kinds of flowers that people are planting. So we decide to put in a little bit of hunting. In other words, we're going to issue so many permits per year to actually eliminate. So we're going to eliminate H rabbits per year. And at first I told you that H was 3 over 80. Since we're measuring things in units of 1,000, 3/80ths of 1,000 that's equivalent to 37.5 rabbits. So, I don't know how you shoot half a rabbit, but but anyway, that's where we are, okay? So now let's analyze this problem. First of all, let's analyze it with the picture, but I'm going to just rewrite this slightly. So this is minus 3 over 80 plus 1 over 10 times y minus 1 over 20 times y squared. And I'm going to write this as minus 1 over 20 y squared minus 2y, okay, and then it'll be plus 3/4. See, this is the minus 1 over 20 y squared term. Minus 2 over minus 20 is 1 over 10, that's that term. And this term is 3/4 minus 1 over 20 is that. Now, let's actually, first of all, draw a picture. And the picture will look something like this. At the right hand, at y equals 0, this right-hand side is at minus 3 over 80. Okay? Then the graph comes up like this and down like this. And we're going to discover now in a minute that this is a half and this is 3 halves. And this is where you guys have a lot of trouble in factoring, in taking this expression and in factoring it. Now, factoring quadratics should be very straightforward because you can use the quadratic formula. But the quadratic formula is essentially just an exercise in completing the square. And so let me do it that way. So this is minus 1 over 20. And this is y squared minus 2y. To make this a perfect square, I should add 1, because then it would be y minus 1 all squared. So plus 1. But if I add 1, I have to subtract 1, and combining that with the 3/4 will give you minus 1/4. So this is exactly the same expression as this. Right? So that's exactly the same expression as the line above. But you see, this is equal to minus 1 over 20 y minus 1 all squared minus a quarter. Now, the difference in two squares, a squared minus b squared, is a minus b times a plus b. So this is minus 1 over 20. y minus 1 minus a half, which is y minus 3 halves. Y minus 1 plus a half is y minus a half. So you see this expression is just the same as minus 1 over 20, and I'll reverse the signs of both of these. It's a half minus y times 3 over 2 minus y. So when it's factored, it's very easy for you to draw this picture. But it isn't that hard for you to draw the picture actually from here either. So I want you to fall in love with the quadratic formula. Be able to factor. All right? Now we're at a situation that this is our picture. What's going to happen? What's going to happen now is if I start here, I will end up at 3 halves. If I start anywhere out here, I will end up here. I'm talking about the blue line now. The red now this is the graph.
Where did you get 3 halves and 1 half? Did you just get that from solving the
quadratic equation? But I did it the way we actually, from first principles. I completed the square. So I have y minus 1 squared minus a quarter. A squared minus b squared. It factors into a minus b times a plus b. This is a minus b. That's a plus b.
So you set, once you completed the square, you set it equal to 0, then just algebraically
Yes.
solve.
Yeah. That's how you get the roots. Yeah. All right. So now, where's the danger here in this ecology? If you happen to start the number of rabbits in this particular little band here between 0 and a half, in other words, if you start at less than 500 rabbits, you're in trouble. The hunting is too much. The rabbits will decay to 0. But as long as you start out with more than a half, that's 500 rabbits, you'll end up at this particular stationary equilibrium for the population. In other words, you'll have 1,500 rabbits. So what's the basin of attraction of this this asymptotically stable equilibrium? Sorry? Who said half? 1 half to infinity. Does everybody see that? As long as you start off y of 0 greater than a half, or anywhere up to infinity after that, you'll end up at the 3 halves position. Now let's solve and get an exact expression for y of t. To solve, it's a separable equation. So to solve for y not equal to a half, or 3 halves, I have dy over a half minus y, 3 halves minus y, is equal to minus 1 over 20 dt. Now, this by partial fractions is this minus this. Now, I think I've seen that you're good enough at partial fractions that I don't have to go through this particular step precisely, but are there any people here who would like me to do that? Okay. So, if I have 1 over a half minus y, 3 over 2 minus y, I write this as a over a half minus y plus b over 3 halves minus y. I multiply across by the denominator and I get 1 is a times 3 halves minus y plus b times a half minus y. Now that is something which is true for all y. So I will choose y equals 3/2. Then I eliminate this term. So I get 1 equals b times a half minus 3/2, which is minus 1. That implies that b is minus 1. On the other hand, to find the a, I will choose a value of y to make this factor 0. And I will get at y equals a half, 1 equals a times 1. So that implies a equals 1. So this is 1 over this minus 1 over that, which is what we have written here. Okay? And this is equal to minus 1 over 20 dt. Integrate. Integrating this will give me log minus log goalposts half minus y. We have to put the goalpost because we don't know whether, well, we know in fact y from our picture, we know y is going to be greater than a half. So we've got to make sure we have the absolute value. So this will be minus log a half minus y. Because of the minus and the minus, this is plus a half, sorry, plus log 3/2 minus y. This is minus t over 20 plus c. Now, combining these two things, it's the log of this ratio. So I've just put this in under here. Log a minus log b is log a over b. Now, to take the log off, I exponentiate. So this is equal to e to the minus t over 20, e to the c. To take the goalposts off, I have to allow a plus or minus here. So it'll be 3/2 minus y over a half minus y equals a e to the minus t over 20. So the a stands for either the plus or minus of e to the c. You see, e to the c, no matter what c is always positive. Now we have to allow for the possibility that a might be negative. In fact, it is, because if y of 0 is 1, say, okay, if we're starting here in the middle, then I have 3/2 minus 1 over a half minus 1. So it's a half over minus a half. So that implies that a is minus 1. Now, if a is minus 1, then I have 3/2 minus y equals minus a half minus y times e to the minus t over 20. Now I'm going to take all the non-y terms over to this side and all the y's to this side. And then I get that y of t is equal to 3/2 plus a half e to the minus t over 20 divided by 1 plus e to the minus t over 20. Is that okay? I got all the y's on one side, all the non-y's on the other, and just solve. You can see at t equals 0, this is 3/2 plus a half, which is 2. This is 1 plus 1, which is 2. So y of 0 is 1. As t gets large, if t is, say, 100, okay, then this goes away, and so I tend to 3/2. Yes? So, why did I change from, here? If I change the sign of this, and I change the sign of this, That's a minus minus. So this is the same as that.
If your equation without changing the minus sign would be the same answer?
Yeah. 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 Question?
Can you clarify how you took off the absolute value sign?
Yes. Good question. So I have the absolute value of this is a positive number here. It's e to the minus t over 20 times e to the c. Now, what the absolute value means is if this expression is negative, I take its minus value. If this expression here, if the y is such, for instance, we start out at 1. If we start out at 1, okay, then we want to make, the absolute value means we want to make this positive. Okay, so the 3/2 minus y, if we start between 1/2 and 3/2, this guy will be positive, but this guy will be negative. So we have to write this then as 3/2 minus y over y minus 1/2. That's what the absolute value means. Okay? An alternative way of capturing that is just to leave this as 1/2 minus y, but allow this guy, this constant here, to be plus or minus. So we do that by just calling him a. The e to the c is a, except now that a can be minus or plus, and we'll discover which it's going to be from the initial condition. And once you determine, if you start anywhere in here, you'll find the a is negative. And it'll stay negative for the whole life of the trajectory. If you started out here, you would find the a would be positive, and it would stay there all the while for the trajectory. Yes?
Can you explain how you went from the equation on the bottom right there to the one on the bottom left?
Yeah, okay. I'm going to bring this term here to the left-hand side. So it's 3/2 plus 1/2 e to the minus t over 20. Equals, this y comes to this side. It'll be y, minus minus is a plus, so it'll be y plus y times this, which is y times that. So I have y times 1 plus e to the minus t over 20 on this side. I have 3/2 plus 1/2 e to the minus t over 20 on that side. And I solve for y. Question?
Yeah, about the graph.
Yep.
So if you issue 37.5 hunting permits,
Yep.
and you start with the rabbit population anywhere under the curve, and you're going to trend towards.
If I'm going to start on this axis. So if I start anywhere from here
That's rabbit population, right?
up to here, up to forever, then I'll end up here. If I actually start at here, I'm in trouble. It'll go back to 0.
With rabbits, a rabbit population under the 1/2.
That's right. If the initial rabbit population is under 1/2, you'll wipe them out because you've issued too many permits. Now the question comes, okay, let's go back and ask the following question. How many permits could we offer and still keep a population of rabbits? All right, so now we're going to let the h be unknown. So I have this as minus h. Okay, now a lot of people had trouble with this step. So I'm going to write this again as minus 1 over 20, y squared minus 2y, and then the minus h will become plus 20h. All right, so you all agree this is the same as that. I will complete the square again because I want to factor this. So this is minus 1 over 20, y minus 1 all squared, because y squared minus 2y plus 1 is a perfect square. It's y minus 1 all squared. But if I add 1 to make this a perfect square, I have to subtract 1 from this. Right. So I have now the equation is dy by dt is this guy. Now before, this fellow, this was 3 over 80, so this was minus a quarter. Because 3 over 80 times 20 is 3/4. So this was minus a quarter. Then we would get real factors, because we could have y minus 1 all squared equals a quarter with either y equals 3/2 or half. We had real roots. But supposing the 20h minus 1, supposing the 20h minus 1 was greater than or equal to 0. So this guy is a constant, greater than or equal to 0. What's the sign, S-I-G-N, of this guy? Positive. So that's positive. That's positive. This is negative. So for all time, dy by dt will be negative. What's going to happen to the poor rabbits? That's it. Goodbye, rabbits. Now what happens here? And we'll draw the one right on the margins. The one right on the margins is if h was 1 over 20. So it comes up and just becomes, this is a double root here at 1. And so the graph looks like this. So this is the graph at h equals 0. This is the graph at h equals 380. And this is the graph at h equals 1 over 20, which is 4 over 80. So if you issue 1 over 20 permits, 1 over 20 times 1,000, which is 50. If you issue 50 permits, no matter how many rabbits you start out with, you're going to end up going all the way back here. Okay. Now all that information could be discerned if you were able to solve quadratic equations. Yes? Right. Right. So because when the square root, when what's under the square root is positive, the square root gives you a real number, plus or minus. When the square root is negative, it's what you're going to meet next Tuesday, complex numbers, square roots of minus 1, which are great things, but not for rabbits. So you lose the real roots. This graph goes underneath, it falls underneath here like this. So this is how, for instance, any control of some ecology, this is how people manage ecologies. There's some equation like this, telling you how, say, a school of fish will multiply if there's lots of plankton or something like that, if there's a big kind of upward plume and lots of plankton, then the fish thrive. But there's a natural saturation level. So you may be given this not as an expression, like simple like y times 1 minus y, it may be given to you as a curve. This is an empirical curve that we've measured. And so you might know this curve, so you'd know this curve, and you'd be asked, well, how many fish, what quotas must we impose in order to keep our fish populations alive? And what you'll do is you take this curve you add in the minus h, and this curve just keeps coming down. And when that curve crosses the axis so that you lose the roots, that's too far. You go back well above that. Yes, question?
Yes, so how did you recognize the critical h of minus 120x?
Right. I look here. I have this quadratic expression. I want to know, when does it have two real roots? Remember when, you must remember this formula, ax squared plus bx plus c equals 0 as roots, and you get them exactly by completing the square. B squared minus 4ac. Okay? What you'll find is the b squared minus 4ac term for this quadratic is exactly, has the sign of 20h minus 1. Okay? Because, anyway, the b squared will be 4, the 4ac will be 4 times this, so it'll have the same sign as the 20h minus 1. So unfortunately, if this is less than 0, I can certainly find two roots. Y minus 1 is plus or minus the square root of that. If 20h minus 1 is greater than 0, I cannot find real roots anymore. And that means that the graph has come down below the axis, which tells me that at any point y, dy by dt is negative, and the population of rabbits will decrease forever. I mean, until they disappear altogether. So, really by just using this simple qualitative analysis and maybe some experimental data, you guys can figure out how to make quotas. No harder than this. But you won't be any good at doing it if you can't solve quadratic equations. So, that's important. So, any further questions? Finally, I'm going to do the example on the quiz. People seem to be having great problems with this. What was it? dy by dt was y times 1 minus y minus 536. Was that it? So this is equal to minus y squared minus y plus 5 over 36. Now you can use the quadratic formula, but I like to just complete the square. So this is minus y minus a half all squared. So this will give me y squared minus twice times the cross product, which is this term, plus a quarter. But since I've added in a quarter to make this square, I have to subtract it off here. So I get plus 5 over 36 minus a quarter, which is minus 9 over 36. I had to add in a quarter here, so I have to subtract it off here. So then this is equal to minus y minus a half all squared, and this is minus 4 over 36, better known as 1 over 9. Now this has real roots, so this is just minus y minus a half minus a third, y minus 5/6, y minus a half plus a third, which is y minus a sixth. And now you can solve that equation. You've got dy by dt is minus y minus a sixth times y minus 5/6. How many people were able to factor that? Oh, not bad. Terrific. So, good. Because you're going to get lots of opportunities in the next week to be factoring quadratics. Great. All right. Now, let's go back to the falling bodies. So the falling body problem. Right. So, we have dv by dt. So here's the ball. Okay. When it's falling, so I'm going to take y positive upwards and v positive upwards. It's going to be under the influence. It's mass times this. The force of gravity is minus mg. And the friction force is minus kV. Notice if the velocity, if you initially threw it up, v would be positive, minus kV would be negative, so the force would be down. When it's coming down, v is negative, minus kV is positive, so as it's coming down, the force acts counter to its motion. It's up. Right. How do we solve this? And we'll take v of 0 to be given as v0. So this is just dv by dt. I'll bring this to this side, plus k over mv equals minus g. Integrating factor. Integrating factor is e to the k over mt. Multiply across by the integrating factor. This becomes a perfect derivative, the d by dt of v times e to the k over mt. So integrating. I get minus mg over k times e to the k over mt plus a constant. Initial conditions. V of 0 is v0. That implies that at t equals 0, that's just v0. This is minus mg over k plus c. So c is equal to v0 plus mg over k. Therefore, v of t is equal to this guy plus c times e to the minus k over mt. In other words, I'm going to divide across by e to the k over mt. So this is equal to minus mg over k plus v0 plus mg over k e to the minus k over mt. So that's the velocity. Now let's take a look. In our case up here that we plotted using the computer, the solution is v of t minus mg over k. Well, we took the g here was 10, the k over m was 1. So this is minus 10, that's minus mg over k, plus 10e to the minus t. Well, in that case, we took the v0 to be 0, so this is minus 10 plus 10e to the minus k over mt. Only k over m, in our case, we took to be 1, so it's just e to the minus t. Is that all right? How do we find y? How do we find the position? Well, we have the velocity. We have the velocity. So to get the position, we just use the fact that dy by dt is v. So we have that dy by dt equals minus mg over k plus v0 plus mg over k e to the minus k over mt. And we have y of 0, we'll say started at y0. Well, this isn't even a differential equation, this is just, we integrate. So y of t is equal to minus mg over k times t plus, or sorry, minus this, which is m over k times v0 plus mg over k e to the minus k over mt plus constant. At t equals 0, y is y0, this is 0, this is all 1, so it's minus m over k, v0 plus mg over k, times 1 plus c. So c is y0 plus this. So then the answer is, the final answer, so the position y of t is y0 minus mg over kt plus m over k times v0 plus mg over k times 1 minus e to the minus k over mt. And that's it. That's the expression, because c is y0 plus this, and so I have a plus times this and a minus, so that's the 1 minus. Now, in your notes, D2L, this sign is wrong. So this is in lecture 7 through 10. I think it's page 7. Change the sign. I think I have a minus sign there by error. We'll change it before the end of term. But please check it yourselves. Okay? So now, for instance, supposing we start off, supposing y0 and v0 are both 0. Y of t is minus mg over k, t, then plus m squared over k squared g, 1 minus e to the minus k over mt. Now this is interesting, because after a long time, this thing tends to minus mg over kt plus m squared over k squared g. So it tends to a straight line. It tends to a straight line with slope this, which in our case was 10 or minus 10. And it seems to be a straight line whose intersection with at t equals 0 is this, which is 10. So do you remember the curve, what it looked like? The curve started like, I'll draw it the way you saw it. The curve looked like this, and then went straight down like that. And if we took that line back up, we didn't come back to the 0, we came back a little bit above it. Okay, so what it looks like, the straight line it's on, looks like as if you started here and gave it initially the velocity, the terminal velocity, and then it'll go on that straight line. Okay, and your curve started here, but asymptoted to this. And the reason it's a little bit behind where it would have been had you started it with the terminal velocity is that it took time, the acceleration took time to speed it up to the terminal velocity. So it's not quite as far down as it would have been had it been traveling with the terminal velocity for its full time of flight. Yes?
Why is it that in the top line of t, the final term is -1 minus e to the negative k over mt, and below that it's +1 minus e?
Sorry?
Saying it's a smudge.
Oh. Very good. All these strange blotches on the board. Now, I think I won't do it next day, but I will do it later in the term. We will look at the case where we are working not just with a slow flow, but a guy jumping out with a parachute. And his equation will be minus g over a minus b over a times absolute value v times v. Now, actually, if you want to, you can just choose values of b over a. In fact, choose g equal 10 and b over a to be 1 over 1,000. And say start at v equals 0. And you can actually use the program and plot the positions and everything. When you're using the program and you have to have this function, this is absolute v. What you write is a, b, s, bracket, v times v. So you would write this guy here as minus whatever the b over a is, times your little asterisk, times abs v, or it'll be y in this case, times v. That's the way you would write that in the program. Don't forget them little asterisks. Right? Now you can see how this behaves. What we're going to do, now you might say, well, why is it the absolute value of v? Why? Because we know the magnitude is v squared, but the action, the force, must be oppose the actual direction of the velocity. So for instance, if v were up, v were positive, we throw the thing up first. Okay? Then that's positive, and the force is negative, which is down. But once the thing turns around, this is negative, this is still positive, this is negative, so negative times a negative is a positive, the force is up as the thing is falling down. So if I put just v squared in here, that would only capture the down bit. No, it wouldn't capture, would it capture? No. It wouldn't capture the down bit. It'd be wrong. Because when I'm coming down, I have to write minus v for this, because the friction force is up. So it's important to see this sign. Now, it's in the notes. The calculations are carried out in endless detail. All the terms are in there, and they're correct. And you can take a look at this one for that case. So, don't forget, sections 1, 3, and 6, you'll get your marks upgraded. Prepare for the trial exam. Come to the extra classes. See you.